electrochemical deposition. Now, this electrochemical deposition, it includes electroplating or what we know as galvanic deposition, then also it is anodizing, plus we have also another process where we do not need any electricity, and that is why it is called electro-less deposition. Now, all these techniques of modification of surface through layering of the surface of the substrate, these are actually take place in atomistic level. That means, if we recall those processes like CVD, PVD, which also occur in atomistic deposition, in that term we have some kind of similarity. However, in this case what is done, it is actually chemical reaction augmented by the supply of electricity, and exactly that is why we call it electrochemical reaction. Now, what we see in this case, this electroplating, that is number 1, and this electroplating what we see, it is actually if we consider a galvanic cell or a cell with the vessel full of electrolyte, then we have 2 electrodes, and in these 2 electrodes, one is going to be the cathode and another is going to be the anode. Now, what is of immediate interest to us, that on the cathode we like to have deposition of the material from this electrolyte. That means, electrolyte would be the source of metal and it will donate the metal, and that will be accepted by the electrode, that means the cathode, and its growth will keep on going. And that is why we call it electrochemical reaction that is taking place on the cathode surface, and this is actually the reaction for deposition of the material. But we can also have anodic reaction. In that case, what is going to happen, that is actually the removal of the material from the anode surface, or it can be a reaction layer that can also form on the anodic surface, and with the result of surface modification. Now, in fact, if we see that this deposition on the cathode surface, that means a reaction takes place at the cathode, and that is also accompanied by another reaction on the anode, and in this case the anode is a sacrificial electrode, that means it is a consumable electrode, and this way this electroplating can be done, and we can have one illustration to have further understanding. However, what is the engineering significance of this process, that also we have to understand. Just like any other process, it is basically surface modification to improve or to augment some of the capabilities of that functional surface. And number 1, which is very common in place, that is actually the resistance to corrosion. So, by this electroplating technique, perhaps we can get one coating, a coating of a metal which can offer a remarkable resistance to corrosion of the bare substrate. Say for example, it is low carbon steel, and if we can have a deposit of chromium, definitely corrosion resistance will go up. The number 2, that is also wear resistance of the coating. In that case, we can also have hard electroplated coating. So, that can be also possible, but there are certain metals which itself can give relatively higher hardness compared to the soft one, that means the ductile one. So, that is also one thing one like to achieve. Then say for decorative purpose, aesthetics, for that also we need certain kind of coating, say for example, silver coating or gold coating and all say palladium coating. These are all the noble metal, costly metal, and these are very well used for aesthetics or for decorative purpose. Then we have also another type of coating, say electroplating of the solder material, particularly this is used for making this all electronic circuit, and in the lids of those electronic component or other places we can have a electro deposition of this solder. So, that means those terminals are coated with this solder. So, we need not apply externally any solder with the soldering iron, and when these terminals are held pressed against another element and heated up, then that coating itself will be the bonding layer, and that can be used for bonding purpose. So, this is another very special application of this electroplating. However, electroplating is also used say for increasing the wettability of a surface. Some of the surfaces they can be quite inert and maybe or prone to oxidation. In that case, to increase the wettability for some surface, we can also put a coating of some of those strategic material by this electrodeposition technique, and thereby we can get the job done as per the requirement. Now, all these processes, the greatest advantage of electroplating process is its simplicity. It is not a very complicated process, and additionally we get further leverage from this process. So, it is actually a liquid. So, we can immerse any substrate of any geometry, and that liquid is going to cover this external surface anyway. Now, after just upon switching the battery on, there will be continuous flow of ions, metal ions on this surface of the substrate, and this ion has good accessibility over the entire surface, and thereby the deposition can be done. So, this is one of the greatest advantage. Now, we have to weigh between amongst the processes, compare the processes. Say for example, we can take this example, chromium can be deposited by PVD, CVD and say by this electrodeposition technique. Now, accordingly, depending upon the geometry, then the coating thickness, the structure of the coating, its roughness, its porosity, adherence with the substrate, the growth rate, coating deposition type, and many more things which are in the objectives of deposition or making this coating. From that we get the answer which one should be the best process to handle. One of the another advantage of this, it is the low temperature operation. Hardly the deposition temperature crosses even 50 degrees. So, naturally most of the elements or metal, those are can be used for this electroplating process. However, what is very important in this case, the conductivity of the material, that is only one condition, but nowadays we have other processes. So, by that say Electro-Less, we can have a pre-coat and then that can follow this electrodeposition. So, even on plastic it is not uncommon to deposit any metal by this electrodeposition technique. So, these are the some of the consideration concerning this electroplating technique, that means the substrate, the growth rate, thickness, adhesion, and its ultimately the functional requirement that should be also taken into consideration. Now, this is actually a basic principle of this electroplating, and what we see here that it is just a most simplest possible and one of the common example one can cite. So, this is actually the electroplating tank consisting copper sulphate. So, it is a copper sulphate acidulated copper sulphate solution, and what we have just like two electrodes, this is actually anode, it is made of copper, and here this is the cathode that is also made of copper. Now, since we use this as cathode, naturally we have to connect this negative side of the power supply. So, it becomes negatively polarized, and this one that is positively polarized. Now, what is going to happen in this case? Now, because of this negative polarization, copper ions that will collect on this surface, and then this electron from this path that will move on this side, because it is actually this copper ion, and this will be going to be neutralized by this electron, and this become a copper neutral copper that will be collected on this surface. However, this electron will flow on this surface, and at the same time as the electron is moves, we have release of this copper ion because of the release of electron, and that copper ion that goes into the solution to combine with this sulphate radical. And in this case what we see that with migration of this copper ion towards this cathode surface, there will be a deficiency of copper in that solution, and that will be continuously replenished. So, that means on this side we have here, it is actually what we can show on the cathode, we have this plus 2E, and that gives you neutral copper, but on this side what we have, it is actually minus 2E, that gives us 2 plus plus. So, this is, or we can say that this is also ion plus electron. So, that is actually the thing. So, these electrons which are released from this anode side, that is going to actually neutralize this copper ion which collects on the cathode side, and this way there will be continuous flow of copper ion on this side which will be neutralized, and there will be erosion. I think we should say it is electrochemical dissolution. So, what we see, so this is actually on cathode. So, this is on cathode and this is on anode. So, both the things. So, here what we see, so that means this is a reduction reaction and this is a oxidation reaction. So, both are taking place simultaneously, and this way we can have electrodeposition over this surface. So, this is in fundamental in principle the deposition, that means same metal can be deposited just by transferring from this to the electroplating solution and then finally on this cathode surface. So, this way this process will keep on going and we have a metal build up on this surface. This is another example of nickel. In fact, we have materials say like copper, nickel, cobalt, silver, gold, palladium. These are the metals of immediate interest for deposition over the substrate surface for augmenting their performance. We can have a particular reference to this gold and silver. Apart from for use as decorative coating, giving that attractive color. These are also used in the pins of all those electronic or electrical goods and product, the pins which are connected to the socket, and these pins are not just made of copper. So, these are coated with silver and gold only to have minimum contact resistance, and those contacts should not have any contact problem at all. So, that is why we know that these are the materials of choice. Now, here what we see that this is actually the nickel sulfamate solution. So, what we have in general, actually just like any coating process, what we like to have just the source material. That means, in this case we have nickel sulphate, nickel chloride, and also we can have ammonia, and with that we have nickel sulfamate solution. And what happens in this case, this is actually the nickel anode, and this is going to be a substrate, say for example a low carbon steel, and from this nickel sulphate we have this splitting of the nickel ion, which will be collected here and it will be neutralized just by the cathode reaction what we see here. So, instead of copper here we have to write nickel. So, that will be the neutralized nickel. Now, one thing also we must look, we cannot ignore that because of this we have here this H2O, and that will be splitted into hydroxyl this ion which is negative and hydrogen ion which will be positive. Now, this hydrogen can create some kind of problem in the coating of nickel. The reason is as follows. If we see this illustration, then this along with this nickel ion, hydrogen will also be, collect here, and this hydrogen can be trapped at this point. So, there we must have sufficient arrangement, good wetting agent, so that this hydrogen can be removed, and this wetting agent will create a surface for immediate adsorption of nickel ion and not the hydrogen ion. So, if for unfortunate eventuality hydrogen gets in, we may not get a structure, desirable structure, and it is going to be the global form with entrapment of hydrogen, and that type of coating cannot be useful. Surface will be very rough, it will be hollow, it will lack strength and all other mechanical qualities. So, there we have to pay attention. Now, mechanism of coating formation. Now, mechanism of coating formation, what we can see, say for example, how this coating is formed. Now, it can be just like one layer formation. So, if we have the substrate, now here we have first layer which gets adsorbed on this, for example, and over that another layer will keep on growing of the same metal. So, another layer will keep on growing like this. It is layer by layer this growth, and it can be also in discrete position. It can be so that we have a continuous layer, the first layer of atom which we have shown here, and we have say over this we have little bit here, little bit here too, that is also possible. So, this is called layer by layer growth, but it is also possible to have 3D crystallite growth, that means 3 dimensional growth, that means every direction, and it will be we can illustrate it like this. So, this is the substrate surface and we have say growth like this. Now, what we have? We have a growth in this direction and like this also it is growing. So, that means as it is growing on this side, it is also growing, that means it is the vertical direction growth and it is also lateral direction growth. This way also it can grow. So, these are the two ways it can grow, but obviously if we like to have uniform growth, then definitely it should be a uniform growth add on process, not just selective sites where this add on will keep on going. In that case, we cannot get a uniform coating, but we may end up with some outgrowth at different locations. So, this is one has to consider. Now, this is one example how this coating grows. So, ultimately this is the top layer. So, if we consider this is the top layer, one thing we have to see, it is actually sphere like. So, we can illustrate this point here. So, if we consider this is a surface. So, on this surface we have some formation in some sites. So, these are the preferable sites, and ultimately this will grow and get jointed. So, it was originally small, but it will keep on growing because this is already embryo is formed, and finally what is going to happen, just what we see here, it was originally rather small and it is growing and another is coming from this side and they are jointed. However, during this joining process we have lot of surface defects and flaws. For example, this is one pore. So, with such we have, I mean, so many pores, it can be easily detectable without any difficulty, and here we can see it is almost like a sphere like thing, and we understand that this is just not like a wetted surface. When it is a wetted surface, properly wetted, we should have a flat, but it is almost coming like a globule. So, here we can show on this surface. So, it is almost coming like a globule and it is not very wetting in nature. So, these are the thing one has to also look in, that how to get a coating with a better uniformity, better flatness and also good surface finish. Now, one thing we have to also look, that what are the process parameters of this electroplating technology. Now, here one is definitely the current density. Current density means on the electrode surface the current is this current is collecting, and the area over which so much of amperage is supplied, that gives the current density. So, per unit area what is the current density, because it is simply the material deposition that will be given by this is this according to Faraday's law of electrolysis, that will be given by Z into Ct, and that is we call it electrochemical equivalent, and then this is actually the current C and this is the time. So, this C into T, that is the electric charge, and this is called the electrochemical equivalent, and this is a characteristics of a particular material. So, here per unit area the current density, that is definitely one of the determining factor. Then comes the concentration of metal in that electrolyte, that means it is mostly a acidic solution or alkaline solution, but if it is acidic solution, say we add H2SO4 to have increase the conductivity of this particular solution, for example, and in that how much material has been added per liter, say for example, that is going to be another issue. That means the rate of growth, that depends upon the concentration of the salt, say sodium nickel sulphate or copper sulphate or nickel chloride. So, that strength of that solution, that is also one of the parameter. Then time function, definitely if we are interested in the growth rate, it is also the time function with what time, what is the thickness of this coating, that what we are interested in. Then comes the pH value, definitely it is actually the whether it is acidic or it is the alkalinity of the solution, that is also influencing the deposition rate, and this one routinely look into that. Then also temperature, little bit variation one can expect with the temperature. However, the thing is that plating, the versatility of the plating is because of its very low temperature deposition, this capability that makes this process is very versatile. So, this way one can look into the various property that which can be controlled by controlling this process parameter. Now, what are those properties one has to look in? Let us see. Number 1, hardness of the coating. This is 1. Uniformity, adhesion, then of course corrosion resistance. So, simply one would expect this thing to be properly controlled. Hardness of the coating means wear resistance of the coating, corrosion resistance, and uniformity of the deposition. It is also one of these aspect one cannot ignore, that suppose if we have such a thing and we like to have, and say this side we put a lacquer to make it passive. Now, we expect this coating to deposit on this surface. So, this is the area where we expect this coating to deposit. Now, what we may expect, it will be something like this because of this sharp edge. So, this is going to be something of this nature. So, it is a non-uniform deposit, and this is unlike of any PVD CVD process. So, here because of the sharp point we have large current density, what we have shown here, this large current density, and accordingly we may end up with such things. So, this is one point one should look into, that this uniformity of the thickness. Now, so far adhesion is concerned, this is also one issue, how to prepare the substrate. So, here also just like a PVD process, we should be extremely careful in the preparation of the surface. Number 1, that it is just not a chemical reaction, but it is physically attached to this surface. So, substrate surface what we need, say degreasing. So, degreasing, so by alkaline solution we must degrease the surface, then it should be treatment with some acid. So, pickling bath, that means it is oxide layer to be removed, that has to be removed, and these are the two basic thing one has to achieve to get a virgin surface, to get a reasonable attachment with this particular surface. So, these are the some key points in the preparation of the surface if one has to get a good coating. Say for example, on stainless steel, it will not be a very easy task because of the reason on the stainless steel it is Cr2O3 for example, and then deposition will be extremely difficult. Say if we have some titanium alloys, it can be also Ti2O3. If it contains aluminum, then also it can be Al2O3. So, this if it is present in some atomic level, then this will become a non-wetting surface and we will end up with this globule formation. However, in certain cases these coatings this oxides are not continuously formed. So, it is partially ruptured, and that is why it is also possible to have some kind of galvanic deposition even on these two surfaces. Now, co-electro deposition. Co-electro deposition means, say for example, we like to deposit, say we can give this example, say when it is sputtering we can have two targets. So, it is actually two targets for sputtering, say molybdenum and titanium. So, with two targets we can have molybdenum and titanium, or it can be aluminum titanium co-deposition is possible. Even say by CVD we can have MoCl5 and TiCl5, both can be TiCl4 tetrachloride, both can be brought to the reactor. We can add something more, and with that we can have a co-deposition of this coating over the substrate surface. So, that is not uncommon. So, in this case, say for example, nickel and cobalt. So, that is one very promising pair, and it find immediate use in industry because of the elevated augmented capability given by cobalt. So, this cobalt actually increase the surface property in terms of hardness, resistance to scratching, strength also. So, in that case the reasonable thing would be to have NiSO4, nickel sulphate and COSO4. So, these are the two salts which can be put in the electrolyte solution, and then we can have a co-deposition of this thing, and there can be other combinations also. So, wherever we find a combination that will be useful, and when they are really compatible, then this co-electro deposition, that is also possible, and in that case definitely this current density, voltage of the across the electrode, then the temperature, these are the few things definitely that will affect the deposition rate or the composition of this one. So, it depends upon the definitely the electrochemical equivalent of nickel and cobalt, and also their respective concentration, and accordingly we have the deposit with certain variation in their percentage, but in principle co-deposition by this galvanic technique, that is also possible. Now, thing very interesting and important that we call pulse deposition technique. So, what is this pulse deposition technique? If we have seen this electroplating, then say this is the cathode and here we have one anode, and the whole thing that is put inside an electrolytic tank. So, this is normally the connection. Cathode, this is anode. So, this is actually covered in one electrolytic tank. Now, obviously, here we have the electrolyte which is filled with this, and here continuous migration and deposition on this side. So, this is because this is cathode, but what can be done in a very intelligent way, that we can have a pulsing. Now, this pulsing means this process is actually interrupted. So, we intentionally interrupt this process, and this can be explained this way. Say this is actually say voltage or current distribution, and that is negative, and this side is positive, and what we have? We have a pulsation like this. It can be something like this. It goes on. Now, this is just by way of illustration. Here what we see, two issues are here. That means, what is the level of this voltage or current which is negatively polarized. So, this is actually the cathode voltage. So, this is the cathode voltage, and this is over a period of time what we call on. So, this is on, and here this is actually off time. So, we can say it is T on and T off. By this interruption, what we see that this material which is deposited, sometime this unwanted or the coating, sometimes there is some contamination or oxidation that can be removed or interrupted, and in principle we can recall this pulse DC type supply in sputtering, thereby this positive we clean the target. That means, the target is cleaned by this positive pulsing. Similarly, what we do, this is one way of doing. So, here it is on and off time, that one has to find out. It can be 1:1, it can be 3:1, it can be even 2:1, on and off type. However, we can do further to this, further illustration is possible just by having a variation here. So, this is negative, that means on the cathode side, and we can keep little bit on the positive side, and then again it is negative and this is positive. What we mean by negative? It is actually on the cathode side. So, let us say it is on the cathode side. So, cathode is this we consider negative. So, cathode is negatively polarized for this period of time on, that we call on, and then it is positively polarized, that we call off period. So, that means, what we see in this case, the process is just not stopped. The process is not stopped, but what has been done in this case, it is rather, it is now this cathode is now used working like one anode. So, recalling this figure, if we see, or we can draw immediately another picture. So, this which was used as cathode, so now it is no more cathode. So, it is polarity is reversed. So, with that, now it is going to be just like one anode. So, with that, what is going to happen, that this material will be sometimes dislodged and removed. So, by that process, cleaning or removal of the contaminated material, or sometimes if there is some oxidation or removal of this entrapped hydrogen, all this thing will be possible by this particular process. And here two issues are there, that means this current, that means current during this on period and this off. So, this is one of the parameter, that means how much we have to have this positive side of this cycle of this curve on this side, that means cathode will be positively polarized, and here this plate, say this is plate A and plate B. Plate A is acting like cathode for this period, and here we have little bit on the other side. So, it is working like anode here. So, this T on and T off, that is one of the parameter, and this is I on and I off, that is the current, and also T on by T off. Now, it is also reported that by this process of this pulsing technology, it is possible to have remarkable improvement in the quality of the coating. This nickel coating or nickel cobalt coating or similar materials which has a all the required properties as a metal, but when it comes like a deposit, there we lose their property, as we have already mentioned, that a porous structure with hydrogen embrittlement, we have non-uniformity, we have a global formation, lot of imperfections are incorporated, and last but not least, large grain enlargement of the grain. So, it is looks like all discrete materials are put together with lot of air pocket in between. Now, to get rid of that, if we have this pulsing, in that case what we have seen, increase in hardness, densification, grain fineness, so these are the immediate thing one can look into. Also improvement in adhesion. So, this is one of the upcoming technology. So, people are more interested in looking into various aspect of this thing and to get one of the optimum value with this pulse frequency. And in certain case also there has been some attempt that normally if we consider this is a DC from the cathode side, over that also one AC can be superimposed. So, this is a DC, over that it can be a like this. So, finally, what we get, it is actually this is the, so that means this voltage is continuously changing, and by that change some results, good results are expected. So, a DC bias with a sinusoidal AC which is superimposed over this polarized bias DC, that is also being used for this pulse deposition mode. Now, we have to consider this anodizing. In fact, anodizing means it is actually what we call electrochemical dissolution. That means, the reaction on the anode side, that is not add on, the material is being continuously donated and anode will lose its mass, that is what we understand. But here anodizing means it is also a surface modification process. So, in this case we do not have a cathode to accept anything. So, it will be a passive cathode. So, it does not interact with anything within the electrolytic tank or the container, but it is actually the anode which is going to be attacked or affected. Now, the whole purpose here is to have a surface modification. Now, we have surface change in surface property or surface characteristics. What so far we have seen by this galvanic deposition, it is add on process. But when it is anodizing, that means it is also a reaction on the anode side, and it is just not an electrochemical dissolution. It will not be continued or it will not be allowed. Before that, the whole reaction will stop. So, let us look into this basic principle. say this is one electroplating bath and here we have one anode. It may be a rod, circular or plate form. So, that is anode, and on this side what we have, that we call, this is called hydrogen electrode. Hydrogen electrode, that means its potential, that means this electrochemical potential of this one, that is at 0. We know that materials can be arranged according to their electrochemical potential, and the electrochemical potential with high negative value means materials are anodic in nature, that means they are prone to this anodic action, and the materials with high electrochemical potential, that means high value, those are cathodic in nature, that means they are inert to this reaction, and accordingly we have a scale, and on that scale we can see that on the extreme we have all electropositive element, those are anodic in nature, that means they have high negative electrochemical potential, and on the other extremity we have say gold, palladium like material which are inert to that they cannot be used so quickly, and they are remain unaffected. And in that scale, in the intermediate, in the central position, that is the location of hydrogen, and platinum, that is actually its electrochemical potential is actually at the 0 level. So, that is the standard electrode, and that we have to use for measuring the electrochemical potential of any material. So, that means if we see a metal and that goes like this plus E. So, this is, if it is a that change in electrochemical potential, if it is positive, that means it is anodic in nature, and it will easily release the electron. So, if we have a positive electrochemical potential, but if we find a metal and we can write similar thing, but here we find it is negative, it means that this material is not at all electropositive, rather it is electronegative, and it is cathodic in nature, that means this material cannot so easily release the electron. So, this way we find that there are certain materials, say for example, aluminum or titanium, these are the metals which need some kind of attention, and attention means protection against environment or atmosphere. So, in this case what is done, we have this aqueous solution of H2SO4. So, that is the electrolyte in this case. So, in this case it will be filled with this aqueous solution, and then what is going to happen when we switch on, if we switch on the battery in this case, then what we find that this is going to be anode. So, here we have this oxygen that will come in this side, and that will try to have anodic action over this surface, leading to a formation of this oxide. It can also go with titanium with Ti2O3, but interesting part of the whole thing is that this layer will be immediately passive layer, and with this passivity no further reaction will occur on this side. So, we can very easily get a thickness of say 15 to 20 micron over the surface of this thickness, and that will become this oxide of aluminum, and that is called the process of anodizing. and this can be also with some addition of dye in this solution, we can also have some coloration of this anodized film, and it can have blue, yellow, some kind of color according to the choice, that can be also done. So, basically it is forming one passive oxide layer by this anodic action, and which makes the thing passive, it becomes non-conductor of electricity. Now, here we have electro-less deposition. So, this electro-less deposition means, in simple language, it is actually spontaneous deposition of metal from a solution of hypophosphite. So, what is their speciality? This, in the plating tank, what we have just one solution of metal, and this one here we have that substrate. Now, this substrate itself, this surface will be catalytic. It is called a catalytic surface. So, here we do not have any electrode, no supply of electricity that is necessary. And what we have actually, say here we have the nickel sulphate solution or nickel hypophosphite. So, basically it is sodium hypophosphite plus nickel sulphate that is added, and this nickel that will be put here, but what is this is actually a reducing agent. So, this nickel will be reduced from this sulphate, and this nickel will be attached to this surface. This will become a wettable surface, and by this catalytic action over this. So, here what we find, that mechanism of electro-less plating, we have generation of metal ion, and this metal ion will be released neutralized by electron, and who will supply this electron? That means, there is one reducing agent, and this hypophosphite that is going to release this electron, and by this addition of this electron on the surface, we get one of the element metal. So, what we see here, that metal ion plus electron, that gives that means, this is really reduced by this E electron, and we get this metal element. So, from this we expect this nickel to come over this surface, it can be steel, very easily it can be handled, and reduction occurs on a catalytic surface. So, here this a controlled autocatalytic chemical reduction process. This way also we can describe this electro, it is autocatalytic, auto adjusted controlled process. And advantage of this electro deposition over this electro-less over electro deposition is that, in this case we do not need any electricity, you have a better uniformity of deposition, a substrate need not to be conducting, and we can have a densification of the coating. So, these are the few advantages one can immediately extract from this electro-less process. Only one limitation is that the surface of the substrate should be autocatalytic in nature. Now, metal for electro-less deposition, we have all the metals, nickel, chromium, cobalt, we can have also silver, copper, gold, everything is possible. But what is advantageous, we find along with nickel, we have little bit of phosphorus also coming from this hypophosphite, and that nickel phosphide, that with little percentage of phosphide, that add to the hardness. Similarly, if we have some this reducing agent containing boron, it is not difficult to have also nickel boride, and in this case that reducing agent is not a phosphorus containing element, but it is a boron containing element, and as a result we have also nickel boride. So, materials as chemical reducing agent, it is hypophosphite that we have mentioned, hydrazine, borohydride, and from that we get this boron for this nickel boride. It is also amine boron, that is also a source of boron. Now, we have two types of deposition. One is called slow mode deposition. Here the growth rate is about 1 micron per hour, and this is one alkaline solution, and this alkaline solution that is good for coating on polymer. But when it is a metal or ceramic surface, we can go for a faster rate, and then the solution is acidic in nature, and this 20 to 30 micron per hour, that is not a very difficult task. Now, here we have some examples of electroforming. That means, this electro deposition can be also used for making a form over a substrate, and then this mandrel can be withdrawn and we can have a freestanding shape over this. So, this electro deposition is not just only for covering the metal, but it is also for getting a freestanding surface. So, this is also another example with a different shape. It is like a taper, and it is deposition on copper that can be also done. This is also industrial application, that electroforming of a vessel having this surface, and there by all this anode array we can have flow of the material, and as a result of that we can get a very uniform surface over this mandrel. Now, with that we can summarize today's topic, that this electro deposition that is based on the cathodic deposition, cathodic reaction on the surface of the cathode, which is one electrode, and here it accepts the electron, and thereby the material is neutralized and it is collected on the cathode surface. So, it is actually the acceptor of the metal ion, and on anode side this electron is released and that is fed back to the cathode side. So, thereby this ion that goes into solution of the electrolyte, and that is continuously replenished. Now, in electro-less, what we see, that in this case we do not need any electric power, or the substrate need not to be conducting, but only we need one reducing agent for reducing of the metal salt in the solution, and only one condition is imposed, that means the substrate surface need to be a self catalytic to have this deposition on that surface, and it can be a slow process or fast process depending upon the substrate, and accordingly we can have alkaline solution or a acidic solution. So, this is also possible to have anodizing the surface by proper surface modification. So, we can have a very passive oxide layer on aluminum or titanium, protecting against it for any environmental damage. Now, this electrodeposition process can be industrially scaled up to make freestanding shape. It is just not on a substrate, and this can be used for making various vessels, containers, or having different geometries.